took an interest in studying how pH level affects the wavelength of max absorption of a synthetic versus a natural dye. To conduct such research, we tested the effects of varying pH levels on red 40 dye and beet juice. Both dyes are similar deep red in color, and structurally, they share a similar number of double bonds when comparing the color-producing valvium ion to the red 40 structure. But the red 40 dye has an azo bond, which likely strengthens the red color of the dye more than the natural beet juice. The independent variable for our experiment was the pH of the solution. The dependent variable, which changed due to pH, was then wavelength of max absorption. The constants were temperature and moles of dye.
As the pH varies, it is likely that the synthetic red 40 dye will reach max absorption at the lowest pH, the sample with the most hydrochloric acid added, and have a longer wavelength of max absorption than the beet juice. Their similar structures and colors would lead to expectations for similar wavelengths and absorptions as stable compounds, but the azo bond in FD&C red 40 dye likely strengthens the red color of the dye more than the natural beet juice. It is stated by Terrific Science Press that red cabbage changes from purple to bright pinkish red as acidic vinegar dressing is added, and red has the longest wavelength, so most absorption. With such information, the red 40 dye would likely have a higher max absorption than the natural dye due to the azo bond with the multiple double bonds at the lowest pH sample. And materials: hydrochloric acid, sodium hydroxide, spectrometer, cuvettes, 450 milliliter beakers, pipettes, cuvette white paper, distilled water, beet juice, red 40 dye, glass stir rod, and a pH meter. That should be all, and we can get started with our procedure.
These data tables are being used to show the pH levels of the dyes as acid or base is added to them, and the varying pH that affects the wavelength of max absorption in nanometers. The values of wavelength for the beet juice were higher than the red 40 wavelengths when they had the approximately same pH, whereas the values of wavelength of pH for red 40 were lower than the beet juice wavelengths. Our results show that there is a gradual shortening of wavelength for beet juice as pH increases or base is added, while values for red 40 at varying pHs did not have a consistent pattern or trend. There was a wider range in red 40 compared to beet juice, so this would mean that the red 40 is slightly more affected by pH. Hello, Professor Reg Borman here, and my colleague Professor Beets, and we are two chemists that will be concluding this experiment. Here we go. The experiment had yielded results that were mostly in line with the hypothesis. The hypothesis stated that the red 40 would have the shortest wavelength of max absorption with the lowest pH. However, the sample of red 40 at the second lowest pH, a pH of 5, had the longest wavelength of max absorption. So the hypothesis was very close in saying that red 40 would have the longest wavelength of max absorption at the lowest pH.
So it would be shorter?
No, longer! Continuing on. Curiously enough, the beet juice had a smaller range between wavelengths of max absorption at varying pHs than red 40. Such information leads to the belief that our eyes can better pick up the complements of the shorter wavelengths as occurred with the beet juice, especially when the purple was observed. Yellow, the complement of purple, would have been absorbed. Human eyes have more difficulty seeing the longer wavelengths of the red, which explains why the red 40, when simply observed, seemed to not really change in color, but in truth had a greater variance in wavelengths of max absorption.
Ah, yes. There were both random and systematic errors associated with the experiment, though. The major random error was that not enough trials were conducted. So, in the future, more trials should be conducted in order to obtain a more consistent dataset. A possible systematic error occurred when hydrochloric acid and sodium hydroxide were added to the samples. Stirring was necessary in order to distribute the acid or base throughout the beaker. When the stirring would cease, the change in the pH would change slower, so it is possible that certain pH samples were not stirred enough, and the acid or base was not distributed evenly. In future trials of the experiment, it would be beneficial to stir for a consistent amount of time, at least 1 minute, in order to ensure that the desired pH is acquired and not skewed by lack of stirring or unequal distribution.
From conducting this experiment, we learned how pH affects wavelength and the limitations of human eyesight. Such could be an important factor for marketing products.
Yes, products using red 40 dye would not create concerns for color change due to pH, while a product using beet juice may change color if pH were not constant, at least observingly so.
Of course, yes. Because the wavelength and max absorption in red 40 at varying pHs are not easily observed by humans, it is a safer option for food and drug and especially cosmetic companies looking for consistent color to go with red 40 and not beet juice.
Alright, beets to that, my friend.
And red 40 to that, my friend.